Welcome and hello. This is a video lesson in HY-8, and in this lesson, we're going to be talking about external energy dissipators. So these are the dissipators that are outside or downstream of the culvert, as opposed to what we talked about in lesson 11, where those were internal to the culvert. All right. So what I have on the screen is my HY-8 program that's loaded up. I'm going to go ahead and right click culvert crossing data. And then to get to the energy dissipators, just come down here and click on energy dissipation button. And then at the top, we have this drop down for energy dissipators. The last one is design external dissipator. The different options here for dissipator type are what we're going to be talking about in this lesson. All right. And those types are drop structure, still basin, and stream bed level structures. Let's go ahead and start with drop structures. A drop structure creates a sudden change in elevation at the culvert outlet, causing water to drop into a lower basin. This freefall breaks the flow's momentum and promotes turbulence mixing upon impact, which dissipates kinetic energy before the water continues downstream. All right, so what we need to do for all of these designs is specify the crossing and then the culvert and then the flow rate. So that's all done already. After that, we have culvert data, which is based on the selected flow rate. And then further down, I'm seeing some red warning messages. So for the selected external dissipator category, I selected drop structure. And then after that, you're going to select the type based on that category. So for drop structures, there's box drop structure and straight drop structure. And let me just click on box drop structure. Okay, so it's telling me that the Froude number is out of range. What you may see when making a selection is restrictions. So for instance, the tailwater information is required and the Froude number needs to be less than 1. So let's go back to our input data. I'm going to change this outlet elevation to something a little bit higher, about 89. Let me see if that works. So I'll click on energy dissipation. Nope, still not good enough. How about 89.5? And it said something about tailwater, so let's increase this as well. How about 89.5? Okay, energy dissipation. All right, that looks good. The red warning's out of the way. So drop structure. There's two different types of drop structure, which I mentioned are here. There's box drop structure and straight drop structure. We're seeing both of these options because it says view all right here. But if I wanted to just select one, you can go ahead and make that selection. For instance, box drop structure, and we no longer have that red error warning. We're ready to input our data, which goes in this form fields right here. Over the course of this lesson, I am going to display a few of the figures. So what you're seeing here is the box drop structure. This is the plan view from the top and the profile view down below. There's a number of different dimensions. So you see W1, W2, W3, W4 in the plan view, and then further down here, length values in the profile view and some height values as well. And then there's also a reference to what each of these distances or lengths represent. I'm not going to go into the details, but I just wanted to show you that here on page 105, figure 6.10 of the user's manual, that's where it talks about the box drop structure. Also, the HEC 14 document, which I'm on the wrong page for, has a lot of information about these external energy dissipators. Okay, so let's walk through the data here. The required drop is between 2 and 12 feet, so let's just leave that at 2 feet. If it was a larger number, we type a larger number in here, but I don't have an actual design, so I'm just going to kind of use some of their recommended values, definitely within the specified range. The next required field is new channel slope to be used with the drop structure, so 0.5% should work fine. And then the length of the box inlet, L1. This is up to the user. 20 feet works fine because that's what I typed in when preparing this for this video. That L1 value is this L1 right here. So if the flow is coming in from the left, water drops down. Here is the L1 distance. The next couple of values involve the width. So like there's a width 1, width 2, and width 3. Next is the width 2 right here, width of the box inlet. 8 feet is what I'm saying. It needs to be greater than 2 feet and at most 8. So that's the maximum. And then the width of the downstream end of stilling basin, 12 feet. It should probably be more than W2 so that there's some flaring out of the geometry right here. So here's W2, here's W3, and here's me saying that I wasn't going to point out what these dimensions are, but doing it anyway. And then the flare of the stilling basin needs to be at least 2. That's this variable right here. And then the length from toe of dike to the box inlet. So if you have a number here, you can type it in, but the user's manual says that if you don't have a value, just use 100. All right, so those numbers are all typed in. I have results already, but if any of the values were not typed in, so for instance, if I just said 0 right there and hit tab, then I don't have any results. I scroll down and I need to put a number in here before I can see any results. So one of the problems with this input form is whenever you type in a number and then click off of it or tab off of it so that that current field no longer has focus, then for some reason the scroll bar likes to push you way up to the top. So I'm just going to hit the tab button once and it puts me way back to the top here. But anyway, if you scroll down, we should have some results. Here they are: hydraulic results, basin dimension results, and dimensions of the head wall. Just like the input data, I'm not going to go through each of these different dimensions or the results, but just want to let you know this is where to find it. And the user's manual and the HEC-14 document will give you more information on where exactly these dimensions are referring to. All right, so the other type of drop structure is up here is drop structure, and then the other type, excuse me, is the straight drop structure. This is page 106. There's a diagram of it. Here's the straight drop structure. You can see the water is flowing down. The straight drop structure would be used in situations where there's more space, like natural open channels, whereas what we were looking at before, the drop box structure, is more for urban storm drains with minimal space, oftentimes contained into a vault where there's no scour concern. However, with the straight drop structure, what we're looking at here, this needs some external scour protection, and it operates with a free fall from the outlet to the downstream. There's only 2 input variables in this form for the straight drop structure, and they're shown right here, which is the vertical drop height, which I have for 5 feet. So some of these values are carried over from other forms or previous times that I've been working on this form, but otherwise you may just see a blank value or a 0 value here that's required. So if you type in a 0 here and then tab, you're not going to have any results until you actually have a valid vertical drop height, which I'll put as 5 feet, hit tab, and then down below, if I scroll down, here are my results. The other input value is right here. This is the channel slope to be used downstream of the drop structure. So we already talked about that with the box drop structure. All right, and then here are all your results and all your dimensions for that external dissipator design. Okay, let's move on to the next category. After drop structure, we have stilling basins. We are currently viewing all the stilling basins, which is USBR Type 3 basin, USBR Type 4 basin, and the St. Anthony Falls SAF basin right here. Just to compare and contrast, a drop structure, which we were just looking at, causes water to fall vertically or nearly vertically to dissipate the energy. But what we're looking at here with the stilling basins, that's where the basin is a horizontal or gently sloped basin that causes a hydraulic jump to dissipate the energy. So if we select one of the 3 types right here, so let's go with USBR Type 3 basin. I'll make that selection. Now it's the only one that's listed, but we have a restriction. It says tailwater and required. So if you see this, that tells you that you need to modify something about the tailwater of your culvert. So I'm going to click on Edit Input Data, and I think it needs positive tailwater here. So I could just drop the outlet elevation too. That should make the same difference. And then let's go back to energy dissipation. Okay, cool. That looks good. So now it says feasible. So tailwater required, but now we have a label here that says it's feasible. So let me go ahead and select USBR Type 3 basin. Okay, it still says required. What's going on? Back to edit input. Okay, I clicked the button right here and it worked. So here are my updated values if you're taking notes. Channel invert elevation is 88, and then my outlet elevation is 87. So there would be starting with 1 foot of tailwater depth. I'm going to go back to energy dissipation, and then I've selected all, and then USBR Type 3. Okay, yeah, so here's the input data. I wasn't seeing this before, but here it is. For USBR Type 3 and 4 stilling basins, the only input we need to provide is the basin width right here. So let me show the figures. Okay, here we are, page 109, USBR Type 3 stilling basin. And what we have is the water is entering the basin, there's chute blocks, there's baffle blocks, and end sill. These are the different energy dissipation devices. That is for USB Type 3. Yep. And then on the next page, there's USB Type 4 stilling basin. Basically, we have the similar structure. We have the chute blocks. We do not have the baffle blocks like we did with Type 3, and then we still have the end sill at the end of the basin. So as you can see here, or perhaps not, there are some dimensions that I'll label here, but the basin width is the only parameter that we're going to be entering for the HY-8 design. So it says that the maximum allowable width here is 9.296 feet. So what we need to do is enter a value here that is less than that. So if I type in 10, for instance, it's giving me this warning. The maximum width of an efficient USBR type stilling basin by the width that a jet of water would flare naturally on the basin force slope. So it needs to be less than that. So yeah, when I put 1 right here, we had a valid results, but I'm pretty sure you can use a number larger than 1. So let's go with, I don't know, 5 feet, for instance. Those look like valid results as well. And if we scroll down, here are our numbers. We have the basin geometry, as well as information about the chute blocks and the baffle blocks. So if we use the same number for USB R Type 4, let's just go ahead and do that. Switch that to Type 4. We'll use a basin width of 5 and then tab off. Here are the results. Here again is the basin dimensions, the chute dimensions, and we no longer have dimensions for the baffle blocks because those are not part of USB R Type 4. All right, and then the last one is St. Anthony Falls. Let's go ahead and break out the image of that. Here it is. SAF stilling basin is what we're looking at here. The 2 input variables required for calculation is the shape, either flared or rectangular, and then if it is flared, you need to specify that flared angle. So let's go back and see what that looks like. SAF basin, tailwater is required. We have that. Here are our different shape options, rectangular or flared. So if we use rectangular, boom, there are our dimensions. And then if we select flared, we need to specify a sidewall flare, horizontal to vertical. And it tells us that 2 is the steepest. So any number in this field that is 2 or greater will work. And that will calculate your dimensions right here for the basin, as well as the different blocks and baffles for that particular stilling basin. All right, we have one more to go. We've done drop structures, stilling basins. Next up is stream bed level structures. Stream bed level structures are built at or near the natural stream bed elevation, designed to dissipate energy without causing a drop or significant elevation change. So we should see from this type drop down of different options: CSU basin, riprap basin, Contra Costa, hook, and USBR type 6. So let's walk through those one at a time. Here is the Colorado State basin. This is my alma mater. Here is an image of an example CSU basin. It's called a Colorado State Rigid Boundary Basin. The restriction is the Froude number needs to be less than 3. And then we need to specify the shape. Another requirement is the shape of the culvert barrel needs to be either circular or a concrete box. That's what I'm using already, so no problem there. But if you get some sort of error warning about the Froude number, yeah, here it is, number less than 3, or culvert must be concrete box or circular. There's no input data, but it will automatically create different designs. And it's currently telling me I have, 1 through 61 different designs. These are ordered in order of increasing width, increasing number of element rows, and increasing element height. So basically, the smaller the number, the smaller the structure, and typically the less expensive. So whichever number you select on here, it will give you the results that were pre-calculated. Next up is the riprap basin apron. So let's go back up to our types, click on riprap basin apron. Okay, so our input data starts right here. We first need to specify the condition to be used to compute the basin outlet velocity. Our 2 choices are envelope curve and best fit curve. You'd select the best fit curve if you expect the downstream flow to be supercritical, and then you'd select the envelope curve if you expect the downstream flow to be subcritical. After that, you need to specify the size of the riprap. So I've already typed these numbers in here, but if you get some sort of error message, which I did originally, you may need to modify your D50 or the max value of the riprap. And then once you have these values in and they're valid, you can scroll down and take a look at the results. The further downstream, the less expected velocity, which you see the velocity decreasing further downstream, as well as the average riprap size. Okay, next up is our Contra Costa Basin, which would be right here. So when you select that, the requirements are the fluid number needs to be less than 3, the tailwater needs to be less than half of the value D. And the values we see here, I'm just going to use the recommended values in this case. So for instance, 3.5 is the recommended value for ratio of baffle block height to block distance from the culvert. The range is between 2.5 and 7. Here's the actual value if you want to change it. Next is the end sill height to maximum depth ratio. So this one really requires a diagram. That's on page 117. Okay, here we go. Here's a profile view and an end view. Honestly, some of these dimensions are kind of hard for me to read. So sorry if they're hard for you to read as well. But what I've found is that the HEC-14 document, which I have loaded up here, but this is the wrong page, that is available through the user interface and typically has better documentation and better diagrams for all of these things that are mentioned in the user's manual. So to access that, you just go up to Help menu, HEC-14 document. That will open up a PDF document, and then you'd have to find where the external energy dissipators are in that document. All right, let's go back to energy dissipators. I'm not sure how this got switched. We were on stream bed level and we were on Contra Costa. We had 2 more input values to go. Here they are. End sill height to maximum depth. Recommended is 0.1, so let's go with that. And then finally, the basin width. This is going to be between 6 and 18. The channel width is 8 feet. Channel width recommended. So if the channel width is recommended, I guess I should change this 12 to an 8. But anyway, I tabbed off. I'll scroll down again. Here are the results using a basin width of 8 feet. We got 2 more to go, but I'm probably not going to go through them. The reason being, Hook required me to put the fluid number between 1.8 and 3. And miraculously, I am already between those numbers. Oh yeah, 1.87, it says right here. Okay, I had the hardest time trying to get that in that specific range when preparing for the video. So at this point, I'm just lecturing on the fly here. As you can see, we have our input data. And then I haven't read this before, but here are your values. We have flare angle in degrees for the basin. Looks like 5.5 is recommended. We'll go with that. Width for the downstream end of the basin, ratio, another ratio, a third ratio. I'm going to go ahead and find this real quick. Hook basin. Here is the hook basin diagram. Yeah, again, similar. It's a little bit too hard for me to read. If I really zoom in, okay, I suppose if I really zoom in and I'm motivated, I could figure it out. But just like the others, type in your input data, make sure it's all valid, scroll down, you'll see your results, you'll see the dimensions of that particular hook basin. The last one here is the USBR Type 6 basin. Scroll up to that. Instead of hook, USBR Type 6. Okay, the dissipator is not feasible. Reason, the flow rate is too high. Let's go ahead and change that. Some of these error messages are pretty easy to understand and work with. Okay, still too high? Oh, no, fluid is now out of range. Oh, okay, it needs to be between 1.8 and 3. Yeah, let's see, we're down to 1.43. So if I make the slope a little bit higher, that may work. Let me go ahead and change the outlet to, how about 86? Maybe that'll increase the fluid number this time. Let's go with USBR type 6 for our external dissipator type. What's our fluid number? Fluid number is 1.55. I thought it had to be, okay. What I remember is that this was another one where it basically did the calculations for you and it developed the dimensions for that particular stream bed level structures. All right, well, that is it for the lesson on designing different external energy dissipators for your culvert in HY-8. We talked about drop structures, filling basins, and stream bed level structures.